In this video, we'll cover acid and base titration. We'll focus on polyprotic acids. Polyprotic acids are acids that have the ability to donate more than one hydrogen, so polyprotic. We're going to take the phosphoric acid as an example to illustrate how the polyprotic acid reacts in titration reaction. So phosphoric acid would looks like this. It's H3PO4, and we take that H3PO4 and we're going to titrate it with a strong base, which is the OH minus. Okay, so that's what's going on here. If you look at the y-axis, that's the pH, and the x-axis is the OH. So in the very beginning, you're only left with the phosphoric acid, so you only have this particular entity in this corner right here. Now, as time passes and you add more and more and more OH minus, it's going to react together. And when they react together, you'll see this reaction occurring. And that's when the H3PO4, it's going to donate one of its hydrogen to hydroxide to form water. And then you see its conjugate base, the H2PO4 minus, and the reason why the negative sign is there is because H has been donated, and so it loses a hydrogen, it loses a positive charge, so hence it's left with a negative. Now, at a region, this particular point in time is where the pH is going to equal to the pKa of the first polyprotic acid. And that's when the concentration of the acid and its conjugate base are going to equal out. Now, and you're going to add more and more base in, and as you add more of the base in, this will start to diminish. The acid will diminish, and at the equivalence point, you're not going to have the phosphoric acid anymore, but you'll only have its conjugate base, which is H2PO4 negative. You'll only have this one. So that's at equivalence point. Notice also that pH is increasing as time passes because you're adding in more base. Now, because this particular conjugate base still has the ability to donate another hydrogen, so here's my another hydrogen, it's going to go into another buffer region in which the H2PO4 minus now is acting as an acid, and it's going to donate one of its hydrogen to the hydroxide that's continuously pouring in, and then it's going to form HPO4. Now it's -2, so another hydrogen has been taken out, so you see the -2 occurring plus water. This region is where the acid, right? It was a conjugate base, but now it's an acid, and its conjugate base are equal in concentration. And also this is where the pH is going to equal to the pKa of 2, okay? The second dissociation constant. Then more and more bases added, and at equivalence point 2 as where in which you don't have any H2PO4 negative left, so you don't have this acid, you only have the conjugate base left. Now you add more and more base. Now you take that conjugate base, it can still act as an acid because it's that last H that could be plucked out and then become donated to the OH minus form water. Then you're left with the phosphate ion, this PO4 negative 3. And so this region is when the concentration of the acid, which was previously a conjugate base, is now equal to its conjugate base. So So you see that equal. The pH at this region is equal to the pKa of the third dissociation constant. Then you add more base and you're finally at the equivalence point. You are completely out of the HPO4 2 minus. All of the potential acid has been all taken care of and now has formed into water. Also, as you go towards this step here, the pH is increasing because you're adding in more and more base. So now that you have some illustration of this polyprotic acid, we're going to go into our learning check. Learning check, this one requires to draw a titration curve for carbonic acid, so H2CO3 with NaOH as a titrant. It says label X, Y axes, and where the acid is equal to the conjugate base, so you need to label those. And lastly, indicate where the equivalence points are located. So we're just essentially going into that previous slide that we just saw, and we're going to be drawing another titration curve with not phosphoric acid this time, but carbonic acid. So let's try. Before we begin, note that the H2CO3, how many hydrogen can this donate? It has the ability to donate 2 of the hydrogens, but we're only going to take one step at a time. Another one we want to recognize before we graph this, let's see what the spectator ions are. And we want to get rid of those. In the spectator ion here, I see that it's sodium, so I'm going to take that out. So we have the carbonic acid interacting with OH minus. So let's go ahead and draw this graph. So I'm going to go ahead and draw the y-axis, and then here's my x-axis. My y-axis is pH. My y-axis pH, and then the x-axis is going to be the concentration of, or the volume of how much NaOH is made, not concentration, volume. So volume of NaOH added. Okay, since we have 2 hydrogens that we can donate, we're going to draw 2 titration curves. So this is one hump here, and then the second hump here. The previous slide had 3 humps, okay? 3 humps. So if I'm going to go back to the previous slide, you notice there's 1, and then 2, and then 3. Okay, if you ever wanting to know how many humps there is going to be this equivalence point. Look how many equivalents there are. If there's 3 acid that it can donate, then there should be 3 equivalence point. But for our scenario, we only have 2, so we should have 2 equivalence point here. This area is not an equivalence point. Okay, so very in the beginning, we only have H2CO3. We only have its acid, but it wants us to label where the acid is equal to the conjugate base. And so that would be at the first buffer region, which is right here. So this is where this is happening, H2CO3. And then that is reacting with hydroxide to form HCO3 minus plus H2O. Okay, so that's what's happening, and that's where the concentration of HCO3 is equal to HCO3 minus. In fact, that's where the pH is going to equal to the pKa of 1. So I'll just write that down, just even though it doesn't tell you to. pKa of 1. Then we go up and up and up towards this area. That's your first equivalence point. This is where you do no longer have H2CO3, you only have HCO3 minus and water. But more and more bases being added, and we're going into this direction. Can you label the rest? See if you can do it and come back. So here's the key. The second learning check wants to know the titration curve. It shows the titration curve for oxalic acid, and it's titrated with hydroxide. What species are present in A, B, C, and D? So let's go with A first. What's in A? Well, hold on. Back up. How many hydrogen can you donate? Yeah, you can donate 2. What's the spectator ion here? Yeah, you can get rid of the sodium. So let's get rid of that one. Okay. All right, now what's in A? A, we haven't added any NaOH here. So this is representing NaOH volume. We haven't added anything yet. So we only have the oxalic acid. So we only have H2C2O4. What about at B? B is that little buffer region where it slants off. And we have said the concentration of here, oxalic acid, is going to equal its conjugate base. So that would be what's present is H2C2O4, and what's present is HC2O4 negative is present there. I mean, you can add water, you can say there's some hydroxide there, which is all true, but I'm actually looking mainly for the acid and the conjugate base. And in fact, the concentration of these guys are equal. What about at C? At C, all of the conjugate acid has been taken over, so meaning it's been used up, and so you're only left with the conjugate base. Again, yes, you're adding base, so the OH minus is there, and yes, there's water there as well, but I'm only focusing on the oxalic acid, the process of it for now. You can put those down, and you won't be marked for it. So you only have this present. So you try D and come back and check this video. And here's the key. I'd like to just take a brief moment in describing this particular graph. It looks very much like the other one, but it's going in an opposite direction. Titration doesn't always involve having acid and then you titrate it with base. Okay, that's what we're used to. We're used to this base in the flask, or I'm sorry, acid in the flask. And then we have the base being titrated. Base. But there are scenarios in which we have the base as a starting point, and then we titrate it with an acid. And the second scenario is what this graph is describing. Because in the very beginning you only have base, you can see how there is a pH that's quite high. Then as more and more acid has added in, it goes down. Now this is also a polyprotic acid it is a polyprotic base, meaning that it has the ability to accept the hydrogen more than just one time. And it's those acid, the conjugate of the polyprotic acid, that allows this to happen. Again, excuse me, again, in the very beginning, you have started with the base, so you have a very high pH. Then you hit an equivalence point, first equivalence point, and then you hit another second equivalence down there. That means it has the ability to accept two hydrogens here as a base, and then it probably became an acid by towards the end over here, a fully protonated acid. And that's all I want to really briefly mention when it comes to this, if you will say, backwards curve, right? Because you're starting with a base.